Here we have a problem on definite integral. That is, we have to evaluate this definite integral and round the answer to 3 decimal places. Okay, what I am going to do is I am going to evaluate this definite integral as an indefinite integral. That is, without the limits of pi over 3 and pi. Once I get the result of the indefinite integral, then I'll plug in the limits over here. That is the lower limit pi over 3 and upper limit pi. Okay, now let me write the given integral as an indefinite integral. That is sin x over 1 positive cosine square x times dx. Okay, now what I'm going to do is I'm going to write this sin x with this dx. When I write this sin x along with this dx, then I'll have 1 in numerator, that is integral 1 over 1 positive, and this cosine square x can be written as cosine x the whole square. Now I write this sin x with this dx and I'm getting times sin x dx. And also let me take a square for this one. Even if I take exponent 2 for this one, still it is equal to 1. Here we have a question. Now, why do we have to take a square for this one? Because there is a formula in integration, that is 1 over a square positive x square times dx equals to 1 over a times arc, let me write the stuff over here, arc tan x over a positive c. Okay, whenever we integrate a function in this form, 1 over a square positive x square, its result is 1 over a times arc tan of x over a positive c. Okay, now to get the stuff over here exactly in this form, 1 over a square positive x square, I just squared the 1 over here. So that here a constant is squared, here the constant 1 is squared. So here a single variable x is squared, but instead of that the trigonometric function cosine for the variable x squared over here. So the difference between the stuff we have over here and here is a single variable is squared over here, that is x squared, but instead of a single variable we have cosine x squared over here. Okay, now to get this stuff exactly in this form, I need a single variable at the place of cosine x. What do we have to do for that? We have to use substitution. That is, we have to substitute a new variable u for this cosine x. Okay, let me do it. Let u is equal to cosine x. Okay, now I have substituted a new variable u for cosine x. Since I have substituted a new variable u for cosine x, now I have to get this complete integration in terms of the new variable u. When I get the complete integration in terms of the new variable u, at the place of dx, I must be getting du. Okay, if I want to get du at the place of dx, what should I do with this u? I have to find derivative. And also here u has been defined as a function of x. So we can find derivative on both sides of this equation with respect to x. When I find derivative of this u with respect to x, I am getting du over dx. And also when I find derivative of this cosine x, I am getting negative sin x. Okay, now to get rid of the denominator dx over here, I multiply both sides of this equation by dx. When I do so, this dx will cancel out. I am getting du equals to negative sin x dx. Here we can multiply both sides of this equation by negative 1 to get rid of the negative sign we have over here. Because here we have sin x dx. Here we have negative sin x dx. That's why I want to get rid of this negative sign. For that we have to multiply both sides by negative 1. When I multiply this du by negative 1, I am getting negative du. And when I multiply this stuff by negative 1, I am getting a positive sin x times dx. Okay, now what we can do is we can plug in the stuff over here in this integral, that is 1 over 1 square positive, and for this cosine x we can plug in this u, then I'm getting 1 square positive u square times for this sin x dx we can plug in negative du. Okay, now what we can do is we can move this negative sign out of the integral over here, then I'm getting negative integral 1 over 1 square positive u square times du. Okay, now look at this integration and look at the integration over here. Both of them are exactly in the same form. At the place of a square we have 1 square, at the place of x square we have u square. Okay, now we can use the result to get the result of this integration, that is a negative 1 over a. For a we have 1, so 1 over 1 times arc tangent x over a. For x we have u, and for a we have 1 positive c. Okay, now let me continue on the next page. So here integral sin x over 1 positive cosine square x equals to, so cosine square x dx equals to, so here we have negative 1 over 1 is just 1. When we multiply this stuff by 1, still we get negative arc tangent, and here we have u over 1. U over 1 is just u positive c. Okay, here you have a question. What do you have to do the use substitution? So because to make the integration process easier, I just do use substitution. So and also there is one more reason. If I want to use a formula in my integration, so I need to get a single variable over here at the place of cosine x. So for that reason also I go with use substitution. Okay, now we have completed the evaluation of the indefinite integral over here, but we got the answer in terms of the new variable u. Actually, u is a variable taken by us. It has to be replaced by the original stuff, that is cosine x. Now we have to plug in cosine x for this u. Now let me write this stuff as it is, that is integral sin x over 1 positive cosine square x times dx equals to negative arc tangent of cosine x positive c. Okay, now I got the result of the indefinite integral, but our aim is to evaluate a definite integral. The original question is the definite integral, that is we have the limits lower limit pi over 3 and upper limit pi. Okay, now here in this integration we can plug in the limits, given limits, that is pi over 3 lower limit, upper limit pi sin x over 1 positive cosine square x times dx. Here I just added a positive c because I evaluated indefinite integral. Whenever we evaluate indefinite integral, in the result of the indefinite integral, always we have to add the constant of integration, that is c. But when I have definite integral, I don't need to add this constant of integration. Now this integration is a definite integral because we have the limits pi over 3 lower limit and upper limit pi. So now we don't need this constant of integration anymore. And also this negative sign will do nothing with the limits we have over here. So now what we can do is we can apply these limits only for the result we have over here. So then we get negative arc tangent of cosine x. So here the lower limit is pi over 3 and upper limit is pi. Okay, let me continue over here. So now in this result, now what we can do is we can plug in this upper limit pi for x over here, because these are the limits of x. Okay, now let me do it. So we get arc tangent of cosine pi negative. Before I apply the lower limit pi over 3 in this result, always I have to take negative sign. Now in the same result for this x, we have to plug in this lower limit pi over 3. Then I'm getting arc tangent of cosine pi over 3. Okay, now we have a negative of arc tangent. Okay, either using unit circle or trigonometric ratio table, we can get the value of this cosine pi. The value for this cosine pi is -1, negative arc tangent, and we can use again unit circle to get the value of cosine pi over 3, that is cosine 60 degree, which is 1 over 2. Okay, now we can distribute this negative sign to this and this, then I'm getting a negative arc tangent of -1. And when I distribute this negative sign to this one, negative times sign will become positive arc tangent of 1 over 2. Now we can use calculator to evaluate the value of this expression. And also you can notice one thing here, that is this expression contains inverse trigonometric function, that is arctan. Since we have inverse trigonometric function in this expression, we have to make sure that our calculator has to be in radians mode, because usually we'll have our calculator in degrees mode in default. In that case, when you evaluate the value of this expression, the answer will be in degrees, and we don't consider degree as a real number because the degree is a unit of an angle measure. So but when we evaluate the value of a definite integral, its result must be a real number. So to get the value of this expression in terms of real number, we have to make sure that our calculator has to be in radians mode, so that it will give the value of the expression which contains the inverse trigonometric function as a real number. Okay, now we can keep our calculator in radians mode, and when I evaluate the value of this expression, I am getting a very long decimal value like a 1.249 04, and it keeps going. But according to the instruction, we have to round our answer to 3 decimal places. For that, we have to look at the digit at the 4th place to the right of the decimal point, that is 0. If it is 5 or greater than 5, we have to add 1 to this the 3rd digit to round it to the 3 decimal places. But here we don't have 5 or greater than 5, we have a number which is less than 5. So now what we can do is we can ignore all the digits over here. Now it can be rounded to 3 decimal places, that is 1.249. So the evaluation of the given definite integral is 1.249.